Yeah.
Well, the topic that I'm going to present is called Pinpoint source of driver attention and distraction in the context of safety. Okay, and I think we don't have a lot of people. I think I can relax, and maybe if I need a little more time, I will use it. Okay, we'll give some background about why we do this study, and also we'll talk about the eye tracking overview of eye tracking technologies and their applications, and give some objectives of our study objectives, and talk about the way we collect data, reduce data, and perform the analysis. Then I'll give some inference of the study result in the context of driving safety. Okay. The background, if when you drive on the road, that's a very demanding task. Okay. You need to. The eye is the main instrument for wayfinding. Okay. And it requires the driver to constantly pay attention to the roadway ahead. Okay. And but even though it's a very demanding task, it requires driver's attention. Once in a while, the driver do distract from the roadway ahead. And there are typically three types of distractions. Or one is called a visual distraction, in which the driver's eyes shifted away from the roadway ahead. Okay. Another is kind of we call it a manual distraction, and that means the hand is not on the steering wheel. And that's the third kind is called cognitive, which is even you're looking at the road ahead, your hand is on the steering wheel, but you're thinking of something else. Okay, and these three attentions there's a balance between these three attentions. If any time you lose the balance, and for example, if you look at away from the road for an extended period of time, for example, longer than 2 seconds, and the literature says you may lose control of the vehicle and run into an accident. Okay, and the visual distraction, there's all kinds of distractions, but distraction is a huge problem in highway safety. And the 2009 data shows that in 2009, distraction alone is reporting factor for 5,870 fatal incidents and almost 500,000 injury incidents. So this is a huge safety problem. And eye tracking technologies, eye tracking study started in the late 1800s. Okay, that kind of research has been ongoing because people are interested in how initially start off how to want to study how people read books, read the text. Okay, and then that kind of research continued for more than half a century. And the breakthrough happened in the 1960s. That's the time when a real instrument was invented by a Russian psychologist and can really track where people was looking. Okay, and then starting in the 1970s, we have all kinds of breakthroughs and all kinds of eye tracking technologies start to come up, and the cost also going down to the path that's in our reducing path. Okay, so right now we have basically we call it main type of eye tracking technology. The first kind is called head mounted. This is something to put on your hand, and this is the earliest type of eye tracking technology is still being used. And another kind is called a dash mounted. This is basically you don't need to wear anything. There's 2 cameras and then infrared flash to the driver's eye, and this is the thing that's this is called dash mounted. And another kind is called a electro. These 2 types, they both use infrared to detect where the driver's gaze vector is. And this type is medical devices measure the muscle movement of the person and use that to determine where the driver is looking at. And all 3 technologies has been perfected to the level that they are all highly reliable. Okay, they can be trusted that to replace your hand to issue commands to computers and machines. Okay, and the Google Glass is one type of head-mounted, and the Samsung Galaxy 4, that's their newest smartphone. It has a dash-mounted eye tracker on it. Okay, and you don't have to use your hand; you can use your eye to determine where you want to look. Okay. So application, there's a very wide range of applications for eye tracking technology. The retailers using eye tracking started to determine how they better organize their shelf to attract more shoppers, and advertising agencies, use this kind of study to determine, where they put their digital board, how they do their advertising. The web designers use this study to determine whether their web display is user-friendly, that it can lead the user to follow the links to where they want them to be, and sports, and so all kinds of activities. Okay, in our study, this is basically the kind of data we're dealing with. Okay, you see that the driver in a vehicle have them drive through either in the lab or on the real road. In this case, it's on the real road. Okay, and yesterday there was a keynote speaker. He said all the technology we need for highway research has been invented for us. We don't need to invent any technology. We just need to figure out how to use the technology. And this is the case too. The technology is there, but this is a very data intensive. In a 30 minutes test, and you're talking about gigabytes of data. Okay, 70 or 60 image frame. So it's there's a huge amount of data, and technology is there, but we need to figure out a way to efficiently identify the things that we want to see. And typically, based on our experience, if you watch a 30 minutes video, eye tracking video, and there's a combined, no more than 90 second combined thing of visual distraction. Okay, so how do we quickly locate those small percentage of visual distraction things so that we can study them rather than having someone to view the videos from beginning to end. Okay, so that's so the objective of our study is to understand the eye fixation patterns and the different driving environment. Okay, and then we want to develop a methodology that will data mining method that will lead us systematically to locate those very tiny portion of eye fixations. Okay, that has a high likelihood of reviewing driver visual distraction. Okay, and this is the equipment that's used to collect the data, and this is the dash-mounted eye tracker, and there's two cameras monitoring the driver's face, and this is the infrared thing that's periodically flash to the driver's face to detect where the driver is looking at. And then outside the vehicle, there are 3 scene cameras mounted on the vehicle. So these scene cameras will record the scenes while driving, and this is the machine that records the eye tracking activity. Okay, this thing collect data at that time, and this machine collect data at about 60 hertz, and this cameras collect at 25 hertz. Okay, and then there's also a GPS on top of the vehicle. So whenever you do this kind of study, you're talking about multiple sensors, and their common field is the image frame. Okay, and then the data collection was done in a medium-sized city. The experiment defined 2 test routes. Each route goes through different kind of road. Okay, there's different. The study was done. This was another study, and they want to study the difference between digital sign and fixed sign to see, how this new digital technology, the digital billboard, attract driver attention. But in this analysis that we have done, we did not consider any of that. We just look at the entire eye tracking video and try to study it, because the driver did not know the purpose of the study. So this is done in a naturalistic driving environment, and we can study whatever aspect we want. Okay, and so each test route consists of freeway, expressway, local road, different type of road. Okay, they are designed in a way that there's equal number of digital signs and static signs. Okay, and we recorded a total of 49 test subjects, but for our study, only the data from 35 test subjects was useful. Okay, and the test was conducted during the non-rush hours. That's why the driver is more relaxed, has the time if they want to And so this is the typical scene of the, for example, this is the four-way undivided row. And if you plot the data point where the driver is looking at, this is what you see. Okay, it's kind of mad, but if you do a 3D plot, this is basically the pattern of how the driver is looking at. And we want to figure out a way to allow us quickly to identify those scenes that has the driver distraction. Okay, so that cloud is kind of messy, but if we measure, we divide the screen into, in this case, 50 pixel by 50 pixel cell. We count the number of fixation in each cell. You get this kind of data. Okay, and the next thing, this is two-dimensional metric. It's still not that easy to analyze. So what we did is you transform all this metric into one dimension of data. Then you sort the data in descending order, from highest to lowest. Then what you do is we color code them. For example, this is between 90% to 0 to 9% of fixation. We count it from the highest number to the second until we reach the 90% point. We color all this fixation, and we make it a green color. And then the next, then we find out from 90% to 95% of fixation. This is in terms of cumulative percentage. Color those in yellow, and then the rest colored in red. So this is the way we color code the thing. We made the assumption that if the driver is looking in the green area, this is where the assumption is they are paying attention to the driving path. If they look in the yellow areas, and we need to examine the circumstance to determine whether they are paying attention to the driving or not. And if they look at in the red area, the assumption is they're not paying attention, they are distracted. Okay, so that's the assumption we made. And the factors affecting the driver's visual searching pattern, there are many factors. Mainly the roadway type, whether they're driving on the expressway, on local road, their driving speed. Okay, they're driving at a very high speed. They probably should pay attention, focus more on the driving on roadway. If they're driving at lower speed, they're probably more relaxed. And then also visibility, whether it's during day or night. Okay, and there are other factors. These are the three factors that we considered in our study, and we divided the roadway into different road types: the expressways, ramps, connection ramps. So these are the roadway types that we determine, and this is how we reduce the data. Okay, we determine, we write a little program to process the video. Okay, determine the pixel coordinate of each frame, and then we do a batch operation to join the GPS speed to the data you process, and then you assign a roadway type to each frame. Okay, and then we clean the data, we remove all the frames that without the green circle, without the fixation, and remove all the samples that with a speed that's below 5 miles per hour or higher than 100 miles per hour, because those may not be realistic. Okay, and the speed is very low. That's probably on the parking lot. It's not related to or near the intersection. It's not in the environment that we want to study. And we also remove samples that if they are coded as other, there's not the specific roadway type. That we also screen out those samples. And next, what we do is we will group the samples by the roadway type, by speed, by visibility, and then we color code the cells in each group using the procedure that explained before. This is how we group samples by speed. We for each type of road, this is for expressway sample. These are the speed distribution. We plot this. We also reference the full speed limit. Then we decide, where's the low speed range, where's the medium speed range, where's the high speed range. That's the way. This is the sample in each group. Okay, we have the low speed, medium speed, and high speed. We have different roadways. And the number you see here, these are for example, this low speed for expressway. These are the speed range. Okay, and these are the number of samples in the day group. These are the number of samples in the evening group. So this gave you the group, the number of samples in each group. And And now we just talk about how we analyze the data. Okay. For example, if we wanted to see visual distraction, and this color coding, the nice thing is it's easily flash out certain areas that you can study. We can study any cell, for example. We want to find out why a lot of drivers looking in this area. Okay. And this is a visual distraction. Okay. This you will see how driver distracted. Okay. There's a sign here. Okay. This is a fixed object. This is just one example. There are many drivers, both during the day and during the evening, looking in this area. Okay. And this is another example. We look at, a different speed range and determine, that there's driver looking in the store, and also we were able to detect this kind of driver distraction. Okay, just by looking at certain cell area, we can quickly determine different events. If you watch the video from beginning to end, this thing will last, less than 0.5 seconds. Okay, but the way we do it is very efficient, very quick. We can identify this kind of event. And another thing I want to point out, we started out by trying to find the visual distraction, but during the study we found out a lot of other information that we can infer. This is the highway express. This is the high speed group. This is the low speed group. Okay. Initially we thought if the driver is driving at low speed, they probably should be relaxed to explore others. We expect this green area to be more spread out, but in reality, when it's low speed, the driver actually more focused on the roadway. Okay, and we want to find out why that happens. And there's different, you'll see different scenarios. This is in the example, is going on the ramp, almost stopped, and this is in this case, you see the ramp is not long enough. The acceleration line is too short. The driver does not have enough distance. This is a dangerous spot. And we also found out, there's many drivers doing this. Even without a vehicle in front, they stop, they wait. Okay, And another example is, this is again on highway. At certain spots, driver speed suddenly drop, and what happened is the sun is shining into the driver's eye and causing the driver to have to slow. These are fixed objects that we can detect, and these are the situation that where the driver's eye is actually focused on the roadway ahead. Okay, by grouping into, if you group it properly, the low speed, medium speed, that will help uncover this kind of event. Okay, and this is on ramp. This is initially we thought this is driver visual distraction, but actually it turned out this is a this is a good driving behavior. Okay, a lot of drivers doing this. Okay, you see it. We look at this area. Their main focus is roadway ahead, but periodically they will shift the eye to here. Okay, very briefly. Okay, this is again a lot of drivers at this same location display this kind of behavior. Okay, and let me play it again. This is also an example where there's a competing demand for driver attention. You see, there's a very bright digital sign here. Okay, but when it's a driving demand, the driver unconscious, they will focus on the roadway rather than this digital sign. Okay, and then this is an example that on a local road, when the traffic is low, the driver will, look at other areas, kind of distracted. But as soon as they got into traffic, okay, and their attention will shift back to the roadway ahead. This is if we look at their fixations, in this area when there's very few traffic, the driver will look in this area. Okay, but once they get into traffic in front, and their attention quickly shifts back to the roadway ahead. Okay, and decision. Driver is distracted when there's very few traffic. Looking in this area. Okay. But as soon as you get into traffic, see that attention is shifting back to the roadway. Okay. And these are the things, the method we use, we can easily identify all this kind of event. And so we study a lot of distraction event or different event, and this is the summary of our result. Okay, we can basically divide the screen into A, B, C, D, and all the other area. Okay, basically what we find out if the driver is looking in this area, that's they are paying attention to the driving task. When they look at this B and the D area, that usually means they're B is they're merging. They need to pay attention. In this case, they need to pay attention to the two areas. So they need to focus on area A. Periodically, they need to, quickly scan this area in order to perform the merge operation. And this is if they have other vehicles merging from the right. Again, this is something they typically do. They will again focus on roadway ahead, but they periodically will pay attention to this area. And when you look at driver looking in this area very close, that typically means that the driver is getting very close to the vehicle in front, and they need to look in this area. Okay. And the summary of findings, using the methodology, we can be very quickly to detect isolate driver visual distraction event. Any location we want to study, we can quickly pick up those videos, and we can identify the frame range so that someone can load up the videos, go directly into those frame range to examine what kind of event is happening. And certain tasks require driver to watch two areas. Okay, and there's a primary area, secondary area, but this is, for example, when you perform line shift merging, we can identify those events, and we properly grouping by, if you do a proper grouping by speed, that will have uncovered a lot of events that happen actually when the driver is actually paying close attention to the roadway ahead. And this is something that if you use other methods, you may not notice. Okay, and we can identify roadway deficiencies, for example, the insufficient acceleration time. We can identify sun glare locations, traffic congestion, all these kind of different events. Okay, and so how that is related to safety. By doing this study, we can establish a library of fake source of visual distractions. These are the locations we know a lot of drivers repeatedly looking in those areas. So once we know this, we can figure out a way maybe to warn the drivers. Okay, and also we can pinpoint those dangerous spots. For example, the sun glare happens in a certain period of time at specific locations. Okay, when the driver approaching those locations, if their speed is not reduced, you can issue a warning that you're approaching a dangerous spot. Okay, and we can locate roadway deficiencies, the ramp. Maybe that's something you should plan to improve those locations in the future. If you cannot improve it in the near future, and maybe you can issue some kind of warnings when the driver approaching those locations. So that's also inference for safety. Okay, that's the end of my presentation. Right on time.
Any questions?
Okay.
The speed you showed, those are actual speed limits, or you measured the driver's actual driving speed?
Those are GPS measure the speed.
Measure speed, okay.
Yeah.
So did you, I know that was not the focus of your study, did you kind of look at it, see what's the percentage difference between the posted speed limit versus at what speed drivers were driving? Or is that something correlation with the distraction?
We did not look into that aspect. Yeah. Whatever speed is mainly depend on the roadway. Some local road full speed was only 25 miles per hour, but the road is kind of in rural setting. They can comfortably drive 40 miles per hour. That's
right.
A lot of drivers will do. Okay, but their driving behavior, their visual searching pattern will not be affected. Yeah.
Go ahead. Okay, clarification. So is there any some distraction differences detected between daytime and nighttime?
Daytime and nighttime, we did not look into that aspect, but it's, we can, we haven't explored. It is whatever object they can see. During the nighttime, for example, if there's a light, suddenly they came from dark background, suddenly there's a light, and that typically attracts driver attention, but very briefly. Okay, but there are certain signs that tend to attract driver attention.
Did you observe or draw any conclusions about drivers' safe use of mirrors, the rear view mirrors?
And I think those B and the D area, that's probably where the direction of the mirrors. Okay.
Just a kind of an overview question, like ultimately the value of this would be to provide baseline information and data to be used elsewhere down the road, but the thought occurred to me, maybe that's a question more than a statement, is that a fair statement that it's a baseline data to not necessarily be used for maybe interactive feedback, like following too close? You know, somebody's following too close, would you kind of envision this ultimately being used in a car, somehow in production, or only just for, at the moment,
Okay, this is a post-processing analysis, but I think the way we do it, this can be implemented in the real system, because once we decipher the driver video searching pattern, we can color code it, and if you use that as baseline and you implement it in the eye tracking system, okay, and in the real time, for example, if we know the driver behavior on this section of road, they typically look in this area. One day you detect the driver is looking in a different location area, and that means it deviated from the normal driving pattern, and you can issue a warning. But at this time, I don't know, the machine, the technology has not get to the point they can perform the old eye tracking data. They were post-process. They haven't. It's possible, I think.
Right. I was just thinking, like, you know, those crash avoidance systems that are out there that are already in cars. They're looking out, like, say, at a vehicle that might be following too close. Warning, you're about ready to crash, or you're following too close. Is there any thought about integrating the visual part, you know, into that, or it's just completely separate as a baseline study? You know, that's kind of what I was trying to get at.
I'm sure that's possible in future, but
Yeah.
I think
It's very close. Right now, it's the eye tracking technology. I think, for example, now the machine can run at half the speed. If we lower the data rate, we use the same time to do the real-time computing, you can. I think we are getting very close to that.
and how accurate it is for all different drivers. When you put it in a production level car, it has to work for everybody, not only a few people. So.
Yeah.
A lot of people wear sunglasses, hats. There's so much different variation, you know. We looked into all that as a maker, and there's still a lot of challenges. There's nothing really perfect at this instant to do real-time processing, which works across different drivers to be able to put it in the car. But you know, maybe in future.
Yeah.
Naomi Bayana from University of Pittsburgh is going to make a presentation to us, and he's going to be talking about rehabilitation. So this is more of a medical decremented driving capability. So I guess as opposed to younger drivers that have great reflexes and great perceptual capability, but no experience and no judgment, and older folks like myself who have managed to survive just because we're kind of safe, but I'm starting to lose it because of my age. It's not a medical issue, it's just age, but here we're talking about drivers and rehabilitation because of a medical issue. So go ahead and please tell us your story.
Thank you very much.
Thank you, sir.
So again, my name is Nahom Bayana, and we're not going to do any updates at this time for Java, but I'll talk about my pilot study with the adaptive driving program at the University of Pittsburgh. I'm almost done with my PhD program, so life is going to get better. Background of this project and how the study came together is part of the Quality of Life Technology Center, led by Carnegie Mellon University with University of Pittsburgh as a core partner. And safe driving was a main pillar of work under the center, and the drive cap test bed is an instrumentation unit that Carnegie Mellon University put together, and that's kind of the technology we brought into the driving program. And that's the premise. This little graph, if it's familiar to anyone, it's taken from a manual with commercial driving, and, a little bit with intelligent transportation systems, the vision of trying to identify the point of when to intervene, when to leave control with the driver, and how to determine this intent to promote safer behaviors and the threshold at when you need to intervene with the control of the car. So we have this philosophy in the safe driving group, and the project I'm presenting today hopes to help delineate that line. The premise: to utilize intelligent vehicle technologies to reinforce licensing recommendations and driving programs, and this is driver rehabilitation programs. And I'll expound, but this is the basic premise. The motivation here is what I've kind of identified as this gap of a decade between when we're good drivers and when we're licensed drivers. It'll happen kind of twice in life if we're all lucky. When teens want to get their license, they have to get the experience, as was said. And so that's going to take time by the time they receive their license to when they're actually going to be really much better drivers. And then later on in life, we'll approach a point when our capability and experience is going to be a little bit of a deception. It's not about the years that you've been driving on the road. At some point, your experience on the roadway changes because you have changes with your body. Whether that's a medical condition or it's age, however you want to view that, when things change in the way that you perceive your own vehicle as well as the world around you, that's when you get to the second gap. And you don't know when it's going to come. I don't have an age on there. Not the goal of the research either. But the ARP has an article where they say we're going to be outliving our driving capability from 6 to 10 years. And so for the ARP to say it, they try to keep their hands clean of any kind of programs that would lead their members and customers to lose their driver's license. So they want to inform and educate the public, but they don't want to put anybody in that situation where they're losing their driver's license. But they put out that statement. And so we're going to see a time out there when we're still living, but we're going to not be able to really depend on driving, or it could come to a critical event. So the setting is driver rehabilitation. This is Amy Lane. She's also on my dissertation committee, but I put this image out there because the video is about to show her again in action. She's a certified driver rehabilitation specialist. Her background is an occupational therapist, and she did this kind of career transition to provide these services in the community. Her job is to take people out on the road, assess their driving capability, and she works with people with medical impairments, people with disabilities, people of all ages, because you can be a 16-year-old with a disability and there's no standard car interface that works for you. She can prescribe adaptive technology, assistive technology, to allow people to use the car with modified vehicle interfaces. But on bad days, she's informing her client that either there's no solution to help them drive for the first time, or as an experienced driver on the road, she cannot endorse or recommend for that person to continue driving. And so I have kind of an eyesore chart. This is just to show kind of some medical pathway, and this was an early medical record review of her program where I tracked all the referral sources, mostly physicians. As I mentioned, the medical pathway, it's a doctor's note that brings people in to her program. The intake to clinical assessment to on-road evaluation. Those who would need it would have training, and then there's a kind of a case resolution. So that shows everything, and this is kind of the easy non-eyesore chart. So you have for everyone who received an on-road evaluation, an immediate indication of a pass versus immediate fail, and this middle group of need training, that could also be broken up into two, where a person who is starting to drive with a modified vehicle interface by definition needs training, no matter what, because that's just not taught in any other school. You will need training, as there's no decision to make that person's going to receive training. There are people who drive the standard vehicle interface who are going to be told they need some remediation, defensive driver type training. So that it encompasses the whole age spectrum. Now, the project that I'm presenting to you is part of that safe driving group, and on the DriveCap testbed is Project Navisection. And this is the way that I summarize a framework of how does Amy Lane, or how do driver rehab specialists make their determination. There's kind of two categories of these driving evaluators, the driver rehab specialists, and then there's the driving schools who would train novice drivers or teens. And there's also family and friends. Everybody has been involved with teaching someone how to drive better. And so you assume someone to be capable until the point where you might have to assist in avoiding a collision. And then at that point, you've determined that person's at their driving capacity with respect to the exposures on the roadway. And this is just a very loose framework that shows if you're observing or monitoring someone's driving, these are the factors that you're looking at to determine if someone has reached their critical limit of their driving capability. And how it looks for sample trip on the road, this is where I link in the intelligent vehicle technologies. You would have the evaluator maybe leave the office, stop to fill up gas, go pick up a client from their home, go on the trip, and then at the conclusion of that driving session, drop off the client and return back to the clinic. This is just a sample, just a day in the life of the driver rehab specialist. So looking at what the vehicle, an intelligent vehicle, will be collecting data any time the car is turned on. That's only that client driving segment right there is the data that we want to even deal with for the purpose of assessing that person. So the Navisection system first segments the data, and then it also would log the driving time. There's a little bit of instruction. You might pause in the middle of the session. So it's also segmenting these instructional periods so you get the actual driving time. The enhancement here, the contribution of the Navisection project is then to enhance the data with the times that the evaluator has to intervene. So any steering assistance, braking assistance, and verbal cues, a spoken prompt to motivate the safe driving decision. And so that's the structure and kind of the definition of Navisection as the driver rehab specialist controller to the intelligent vehicle. So that's a lot of buildup. Basically, here's the summary: an integrated technology for driving programs to collect measures of driver capability and reinforce licensing recommendations. And so that links back to the premise and informs how to integrate or how to decide when that data gets infused into the reporting process. And here's a little demonstration. I hope sound is working. I was turning it on and off. I'll play it at the end, but that gave you a visual. Steering assistance and braking assistance is what was demonstrated in that visual. So I'll play it again at the end of the presentation. Now
How
to
does braking assistant work?
So pretty much any driving evaluator has a secondary brake in regards to the evaluation vehicle. I just applied a switch to it to take note of when that event takes place. I used this image from the Road Safety and Simulation Conference, kind of the fundamentals of understanding crash risk. And now with Navisection, I tried to see how well does it match up or fit within these standards or these proven methodologies of research for understanding crash causality. Now, putting in the context of driving school, you're going to experience a lot of driving errors. So it's a rich source to look at driving mistakes. If we look at driving simulators are available in some programs, and measurement technologies, we already know about intelligent transportation systems and new vehicle sensors that can inform our models. Now the question is, how well does this navisection methodology complete this construct? And it comes into the question of whether or not an instrumented on-road driving evaluation reflects naturalistic driving, and then can we take that data and kind of replay it in the form of a driving simulation. It's just kind of an animated driving simulation, because you've already had the actual experience on the road. It's the same thing as a very high-priced driving simulator in terms of the realism. You're actually in the car, and now can we replay that to the clients and students? The question is whether or not the assistance from the evaluator would qualify as a surrogate measure for crash safety, and whether or not having a supervised driving session can be considered as naturalistic driving. Fundamentally, it's not, because there's someone in the car. It's not just natural driving. So it kind of, navisection is a methodology that's a little bit removed. It's better on some things, worse than on others, on both categories of naturalistic driving and driving simulators. So it's kind of this thing in the middle that I'm proposing. But this is an attempt to say that safety management also will have to include recommendations on driver licensing, and we have these fundamental methodologies that can really help in this safety management aspect. So the vehicle setup, there's a lot on there, and I'll say the blue and the green all reflect contributions from Carnegie Mellon University and represent these intelligent vehicle systems, the technologies that enable a lot of those capabilities. What we have in orange is part of the navisection system project, which is helping to detect the steering, the braking, and the verbal cues. The data that I'm going to present, or just the results of this, I'm going to present reflect the navisection system, and the visualization efforts for the future would be to kind of fuse all of these data sets in order to understand what took place when there was assistance, look back into all of the data from these sensors and the other logging systems to inform what actually happened. Is that something that can be trained out? Is it just a bad habit? If it is linked to something medically, is it something that can be compensated for and trained to do differently to avoid that driving behavior? The people we worked with, this is a small, the pilot demonstration of the system was with 20 people, mostly people age 50 and above. It was 80% of them. A quarter of everyone had experienced stroke prior to coming into the evaluation. You see cognitive, motor, medical needs with a lot of the others. And then 3 were actually procedural. There were 2 people who, as a part of their occupation, were driving, so their employer asked them to do this every 2 years. And then 1 person was actually referred by the state. So random sampling technique in the state of Pennsylvania. So those kind of procedural, not really that they had a medical issue. You could say it was just age. But at some level, they needed to be addressed. We have, I exclude, it's n equals 16 for the people who actually drove with a standard vehicle, so we're not comparing between a modified interface and a standard vehicle interface. With the 16, a standard driving session is about 40 minutes, and out of these, we identified 28 instances of assistance for these clients during their initial driving session. We tested my system, since it's not a commercial product. I was a witness in the back seat during their driving session, and in the center column, the dual detection reflects when the system picked up the event and I witnessed the event and entered it manually. To the left is where I missed, as a witness, I didn't enter that event, but the technology was able to capture it, whether it's the steering or braking. So there's only 1 or 2 instances where the system didn't capture the event, but also looking in the evaluator's documentation, we're able to kind of triple validate whether or not these instances occurred. The not so nice result was with the verbal cues assistance. These were both manual entries, one by the evaluator and one by myself, and we didn't agree so much. So we have to really get at what is the verbal prompt or cue that needs to be captured. The way that we treated it for the study is that we were both right, and so we're going to adopt all of those events as things to look at into the future. Now, the correlation between passing or not passing. I don't say that's failing, that could be people who need training. And you'll see that. So the red dots are people who did not pass, and the black stars are those clients who passed. Just by binning everyone who passed, we can look and see the relevance of these detections and if there's any errors in classifying who passes or doesn't pass. So the tally of all assisted events is a physical assistance plus those verbal assistances. And the duration of assistance is only for the physical events. So grabbing the steering wheel or stepping on the brake, we just add up how long were those signals on and how much was maybe the severity, a small indication or a partial indication of the severity of those events. Of course, we need to incorporate speed into that consideration. But the navisection system only looks at the event, and then the vehicle-based information can flesh out the rest of the story with those events. So I'll show it on another figure, but you'll see the red circle on the right is there with no physical assistance, but ended up not passing. So that's purely off of verbal cues, off the prompting. Then the instructor just had to recommend that this person was not safe to drive because of how many events were due to prompting instruction. If you look at number 20, on this column you'll see is about 6 verbal prompting events that occurred with that client. And so you need, it's not just that physical intervention, you also need to track that communication between the instructor and the client. Just to point that out because covered so many of the cases, yet there is a case where they don't touch the wheel, they don't step on the brake, but they have to say this person can't drive yet. In terms of, this is medical, comparing the on-road actual detection of driving incidents to the top left is the American Medical Association guidelines for addressing driving-related skills. Used a battery of 6 clinical tests combined to look at people who were within normal limits or beneath normal limits on vision, motor, and cognitive tests that were used by the adaptive driving program. The second one is a self-report of past involvement with a citation, ticket, or an accident. So you can see that while there might be a little bit of correlation, it's just a lot of error in terms of classifying who's going to pass or not pass the driving session. But capturing the metrics for navisection actually allows you to correlate perfectly who passed and didn't pass based on the evaluator's recommendation. So it's truly a measurement of driving capability and not a predictive factor. It's what we see on the road. If we can do that on the bed of intelligent transportation systems and sensors, this would be really powerful for how you refer people into the system to really evaluate their driver's license. Otherwise, you're having up to 30% error. 1 in 3 people would be falsely told you need to be assessed because of a medical or past driver history records. So this speaks to the evaluator's potential for not putting enough information in the documentation. There were 6 instances where perhaps it said the client was assisted, but it didn't say if it was steering or braking. So just off of medical records, you can't always detect what type of intervention took place. You'll just say, I assisted my client. So this provides, it's also a value to the documentation. And there you can see participant 20, not applicable for either type of assistance, but those were the verbal cues I spoke to earlier. The main findings here, capture data that best correlates with the evaluator's recommendation for on-road driving capability. It reinforces and enhances the documentation to prevent any missing data or recall error. We actually document these crash critical events at a rate many times greater than naturalistic driving studies, where you have to look at the video or use sophisticated statistical analysis with ROC curves to try and drive at those events, but here you have the person in the vehicle to tell you that it occurred at a rate up to between 8 to 10 times more frequent detection of these events because of the setting. And that was compared to the 100-car naturalistic driving study. And then they're not rare, these driving events. How many times does an evaluator grab the wheel or step on the brake? It happened with half of the clients in the study. So now I do my best with the visualization since I'm at the visualization conference. This is looking at the braking assistance in a way to try and communicate this to clients. It's, as I mentioned before, I was the witness in the back seat. Both the evaluator's brake and the main brake line were monitored automatically, and we did a correlation to see when was the brake engaged and when was there assistance by the evaluator. Everything on the next slide just uses the standard, the same length of that arrow, that black arrow. Doesn't matter how long the braking event was, but it's just to show the relative reliance or assistance provided by the evaluator. And it looked kind of like this with the braking assistance. We can look at the driving context, what traffic sign was applied or applicable to that driving maneuver, and how much was the assistance provided by the evaluator. The idea is starting from here to now build that information from the vehicle sensors to tell what was the speed along this timeline, and really, forward ranging radar, what was that headway gap, and how do you start to layer all of this on top of the actual event, like the indisputable event, and provide it as client education. So that's the next step that we're looking at. Apply that speed profile onto the braking event. You'll know when the brake of the vehicle was engaged, when assistance was provided by the evaluator, and with the context of that continuous speed profile. So you really get a sense of severity of the event and frequency of these occurring during naturalistic driving. And then you can just break it up into, are you braking independently, are you relying on assistance, or did you fail to brake? And I think these correlate really well to braking assistance from advanced driver safety systems, and it would be something if correlated and kind of proven within the driving programs with respect to driver licensing decisions. This would really wake up people in society and be kind of the data that moves them to deal with the issue when the time is right. We don't want to just worry people continuously, but when the time is right, if it's the same standard that's adopted and embraced within driver licensing, then maybe it'll kind of move people to do the right thing. So future thoughts, the value of crash critical data and personalizing driver education. We see a lot with the telematics industry and how they're informing insurance and automotive manufacturers. If we can bring those devices into the driving programs, you can have the auto insurance industry able to view data from people beyond their policyholder membership. And for the automotive industry, if you can bring those technologies into the driving program, we can actually correlate when did the evaluator intervene and when was your system going to kick in and intervene. And in that way, when a parent takes their child to a driving school and they say, we know this automotive manufacturer's vehicle is used and endorses this driving program. I know how many times the evaluator saved my son's life on the road, and we know that this vehicle technology actually would have done the same thing for my son. This becomes a more powerful way for society to say, hey, this is going to save my child, this is going to save my mom or dad or uncle, and then this is kind of another way to consider putting out the value of saving lives more than just saying, oh, there's this many people who died last year. This is the #1 killer of teens. Just bring it home and go through that experience, give people that test drive when they take their driving test. This is connecting to another fundamental of driver safety education, a concept called driver narration. It's looking at the autonomous driving. If vehicles can make the decisions by themselves, can they educate new drivers by saying, I'm making these decisions. I'm about to change lanes, I've checked here, there's nobody in this spot, I checked the traffic sign, I've looked at the lane marking, you can do passing here, and the act of the vehicle explaining the decisions to make is an actual practice in driver safety education. You can talk to driving instructors. They may not know the terms driver narration or conversational driving, but these are principles in driver safety education, and it's something that technology can do probably right now without much luck. And then the last piece of personalizing driver education, this is the Pennsylvania Rules Manual. If we can take those figures and actually animate them according to your own driving on the routes that you drive over, does that make the rules more and more pertinent to you as a driver, as an individual? And so that's kind of the vision that I have with the navisection system. Some acknowledgements to my lab, the Human Engineering Research Laboratory, the Quality of Life Technology Center. The work was sponsored by National Science Foundation, and again to acknowledge the Adaptive Driving Program, which was the basis of this work. My dissertation committee, Dr. Cooper is the director of the lab, Aaron Steinfeld from CMU, Kate Steelman as a disabilities expert, Tom Songer as an epidemiologist, and Amy Lane, who was the star of the movie. So thank you very much. We'll take any questions.
Quick question, do you think the assisted driving that's going into newer vehicles such as the assisted braking, is that gonna make it harder for teens to learn to drive? Because, it's also, driving's not just cognitive, and you mentioned something about the process might be able to alert people when to make decisions to do brake, et cetera, but it's also memory, muscle memory. And you have to learn that by route, there's no other way.
I think that I actually had a meeting at NHTSA to discuss this methodology and how it worked, just to get some feedback. And it was one of the comments, I was asking them, well, what's with the recommendation by the National Transportation Safety Board to mandate collision avoidance technologies? It's like, well, our rulemaking group doesn't act so quickly. We have to really consider all the implications, and that was exactly one of them, is my own concern as well. I think with cars, kind of like the comparator to bikes, you can start off with training wheels and then progress up. If we use these intelligent transportation systems, advanced driver safety alert and assistance systems in that way, I think we can, if it's just applied, there's still right now, you turn the system off if you don't want the beep or you don't want the alert. So if we have some way of dealing with that, then I think it could potentially have no problem. But it's tricky, I think.
One of the slides you showed of the scenarios where the highest driving assistance or the braking assistance versus the lower. So in that slide, it looks like when the older people are turning left is where they're having the hardest time, correct?
I've seen that with many studies.
So
That and
your study also shows the
lane
same thing?
keeping, lane tracking is another big one.
Okay, so lane keeping or lane changing? Because I think the data you showed, number one was a left turn and the second was a lane change. In one of the slides you showed.
I can look at it here.
Well, left-hand turns, older
Yeah.
folks are overly involved in left-hand turn accidents, and that has a lot to do with, their vision. Not, depth perception is a big one, as well as being able just to detect and properly understand closure rates, right? So what permits me to reach out and catch baseball, you're losing that as you get older because the capacity of the retina to measure that closure rate dissipates with age. But again, it's not age, it's not at 55 you can't do that. It's that function or that capability varies from person to person.
I have a question. I know you talked about the whole idea is kind of like to drive this down maybe to ultimately to the actual driver's license requirements part. Did you have any sense for what kind of roadblocks you might have, or what is the process for actually changing that from a from a policy or sort of human perspective? Because once you get the technology out there, Yeah, it's like, most of the time, technology is not the issue. It's dealing with people trying to play in the sandbox and getting through all the bureaucracy to make something happen. I know that we, in North Carolina, where I'm from, work very closely with the State Highway Patrol, who are responsible for, reducing their portion of, as enforcement arm of the Governor's Highway Safety Program in this particular case. The state level Governor's Highway Safety Program, they have measurable goals they want to reduce. One of those things, of course, is older drivers as a measure. And if older drivers could be tied to, obviously there's the three parts: education, enforcement, and engineering. On the education part, hey, this could tie right into that. You can get, if you were able to measurably show in some way that changing such an existing program from a partially or all perception-based system or subjective-based system to include some kind of measures empirically in the car would or could ultimately affect those outcomes of reducing, say, older crashes, then, hey, maybe there's an opportunity for tying these all with the safety programs at either the state level. I didn't know if you have any experience with that at all, or if this
I have
is like...
personal anecdotal conversations.
Okay.
I did go to AMVA and speak with the head of at-risk driver programs. He's now the business solutions guy. But as just a general thing, regulatory action with the technology might work with teens because they're still under parents' rule.
Right.
And they're not the biggest, strongest voting bloc
Yeah.
in the population. This is just kind of off-the-cuff comments.
Right.
For older drivers, even the state doesn't want to be a burden because these are people with money and disposable income and need to be, engaged in society. So they have to approach it lightly, and if they do something cavalier, then it'll be voted out.
Right.
I think it has to be kind of more grassroots effort. If there was a way, like I mentioned procedurally, there was a person who was just given a letter, you've been randomly screened to go take the test.
Right.
What if you give someone the option to not be drafted into retesting by using some telematics, by getting an advanced vehicle with ADAS and all the capabilities? If that's something that, I think that's an approach I'd like to explore, and that's a good way to do it. If you can't regulate it, that's kind of my recommendation.
It is a tough issue.
Yeah.
I've been involved with it for a couple of decades now at Federal Highway. Gee, you don't want to put the physician in the position of being the guy that calls, balls and strikes and who's in and out. And but it's going to require community kind of effort, and hell, just coming up with the requirements, the functional requirements of who should and who should no longer have a ticket to drive. And now with these various capabilities, these technology capabilities, maybe you can provide some assistant training or assistant driving. So it's a moving target, but it certainly is not a simple one, and
Well, I'd
it's
like
going to
to,
be a while.
at a minimum, just kind of keep up with the progress of this. Just, is this the only program that you're aware of that is doing this, or are there many, or?
I mean, as best as I can tell, I was always told never say we're the only people who do this when you defend your dissertation.
Yeah.
It's never been done before.
Yeah.
It's being done, we know, with teen drivers. There are pilot studies like DriveCam,
But not
maybe a
super.
decade
Got
of doing this. But trying to advance it systematically,
Yeah.
I think everybody's trying to.
Not to crack.
Okay, thank you. Thank you, Doctor.
Well, as
Give the show
Joe mentioned
a
before, I'm Jason Williams, and I'm the lead contractor for our site at the Federal Highway Driving Simulator, which is part of the Human Factors Lab at Turner Burbank Highway Research Center. And so in that, talk a little bit about the simulator. Well, first, the federal lead here is David Yang, so if you have any questions for the federal programs, please contact him. And of course, he'd be willing to talk about any kind of cooperative work that we do, because we do a lot of cooperative work with both universities and DOTs and localities. So the driving simulator that we have is actually a fairly high-end driving simulator, especially for the visuals. We do have 3 new front projectors we just installed. They're 4K projectors each. So they actually take 4 separate inputs to each projector to drive them. And they are equal to 4 high-def displays. Actually, it's slightly more because they're slightly higher in the vertical than regular high-def displays, which would be 4096 by 2160 is double what the normal 1080 is in the vertical, but this is 2400 in the vertical instead. The barcode projectors are also very good at doing cylindrical warping, edge blending, and we have an auto alignment system that keeps the color absolutely the same as long as the life of the bulb until we change the bulb. And we can set that so we don't set it to the maximum burn rate for the bulbs. They're very bright xenon bulbs that put out a lot of heat. What we can do is, so we have the exact same image for every participant that we run through the driving simulator continuously they last about 6 months. We have 3 rear view panels that are high brightness for daytime viewing. They're essentially the same type of stuff people have in the vehicle, but we're using those as high-end rear view displays. 6 degrees of freedom of motion. Last winter we put in a new motion base. It's a full 6-stop motion base, and we have full sounds for the engine, road noise, wind sound, and of course our simulator, instead of just doing all video recording, we actually use a process that we can replay any scenario anybody's driven just by plotting where they had actually driven. We have all the control inputs and everything recorded forward. So this is a video. This is actually a video we created recording the actual images from our old system. This was the 5 projector system that went by in the beginning. You can see it was 5 projectors. So our resolutions are better than this now. This is a virtual car, so this isn't actually a real time, but we did take 60 frames a second video for the mirrors as well as the full front on the screen, so you get an idea of what it looks like, the video. Shows pretty good. In fact, here comes a train. This is a at-grade road crossing demonstration we did with our railroad administration. The waves that you see is because the screen's not perfectly flat. It's actually not in the video here. So I'll go forward. So this is an image of our new projector systems, and you can see that it looks a little crisper than the old. Now we're going to recreate the video like we just had, so we can show that off more full glory. But the other thing I'd like to mention is some of the videos and stuff you're seeing here is not as crisp as they'd really look because this projector is limiting. The limiting factor of showing the visualizations. So the types of activities that we do is both human factors research, which is shown on the bottom here, behavioral research, so that we go into the manual uniform traffic control design and help determine for both signage and pavement markings on understanding. So the engineers have a concept for whenever we got changes and new things. And we put the human in the loop then in the driving simulator, see if they behave the way the engineers think it's supposed to, and then make recommendations, and the final outcomes of those studies do go into the manual. And then we also do some visualization work, and then sometimes we get a trade-off, and the behavioral studies also work as visualization, and they work together, such as you'll see some examples that we've done with divergent diamond interchange, where we did a visualization to help the public accept the design before it actually went into a behavioral study, where we then help determine the correct signage for the type of intersection. What I'm going to be speaking about next really is the projects that we've done recently that we've had to visualize, and some of the techniques we had to do that were a little bit challenging. So this is really the recent projects that we've done. Minnesota is you've seen, if you went to Wei's presentation yesterday in the R-Cut, I'll talk about some of the techniques we use to create the scenario and the scenes to create the visualization. And then we have some sign distraction studies that we've done. I can show you some examples of that. And active traffic management. We have an active traffic management, and there are some challenges there in creating the dynamic LEDs. And we have several exploratory advanced research studies that we've been working with. And this is where we come in working a lot with partners for universities or other agencies. And we've had recently a dilemma zone experiment that I don't really have any slides for here because we're actually just starting that up right now. But I do have a previous year study we did before that we presented something at TRB 2 years ago on making simulators more useful. We actually ran the same scenario with 3 different leading US simulators. now speak a little bit about some potential future work we're going to be doing. So the challenges involved in creating some of these driving scenarios is not just that we have to do these not as a post-process, creating a video, we have to make this real-time interactive. And that makes a lot of challenges to try to get everything to look right in the first place. And in doing this, we've had the challenge lately of adding in realistic heavy traffic. Very few simulators really do a lot of heavy traffic because it's really hard to make cars that are close to you look realistic and be able to drive with them, have good gap distance, and have the counts that are required for the requirements and scenarios, the things that we want to study. And as we get into some of the type studies, which is more based on connected vehicle, gap distance and things like that become a lot more important, and also having adjacent vehicles in the scene. The other thing is that I can show you, that this isn't as new, but we've got some processes where we take advantage of the other existing software open capabilities out there, such as we use Google Earth, and we're going to be starting using Esri a lot more in some of their products to actually generate some of the real-world representation of the data. But we have to match that with engineering design still, so we have to piece those things together, and I'll show you a little bit how we do that. Sign legibility, this is why we upgrade to 4K projectors. We need to actually achieve closer to realistic distances, because the technique we've had to use before this is we still maintain calibration of where the drivers in the simulator can read the signs, but we have to do that by oversizing them previously. Now with the new projector systems, we don't have to oversize them as much to get the same type of distance reach legibility. So I'm going to first go into where we're linking VIS-Sim as a traffic simulator. Now, there's several reasons. We actually create an interface that can link more than VIS-Sim, but many of the other microsimulation software packages had some disadvantages where VIS-Sim had good advantages. And these are listing some of the advantages we had here is that we didn't really want to get into the process of doing all the programming to reinvent the wheel of trying to create microsimulation algorithms for timing on the lights and all the other. We wanted to reuse something that somebody else did. So we were looking for one to use, and we found that in our own lab, in the safety office and the operations office, they were using VIS-Sim very heavily, and so is most of the community, it seems, in the US at least, and Europe too, are starting to use VIS-Sim for a lot of operation type studies and throughput studies and even safety design studies, and so it worked well from that standpoint, because then we can try to reuse the scenarios already built. We also have the ability in VIS-Sim that isn't there in all the other competing simulators. And I'm not trying to say VIS-Sim is the only solution either, but we do have external vehicle models that we can put in there so we can have additional controls over what VIS-Sim's own updates on the vehicles are. And we actually, in the process, we actually got very good customer relationship with them, with the development team itself, with PTV America, to actually make some of this happen. So we create a real-time interface, which isn't just recording a VIS-Sim scenario and then playing it back in the simulator, because the problem with that is then you have trouble trying to figure out how to do interactivity still, create gaps where the driven vehicle is. So what we've done here is we've actually, in the loop, we can create vehicles that are controlled by the driving simulator that are then positioned as VIS-Sim vehicles in VIS-Sim's own network. So that's unique, I think. I don't think anybody else has done that yet. There are some usages that use pre-recorded output from VIS-Sim. So I'm going to show an example of our VIS-Sim integration here. Where's my cursor? Now, this is one of the videos that's a little longer, so I'm probably going to truncate it a little bit. But so we use two different workstations to generate our traffic from different workstations for VIS-Sim. So we have VIS-Sim traffic control computer separate from our image generator. And this will work across our whole cluster of computers, because our Archer system is essentially our cluster control program. It runs everything. It runs across multiple computers. And you can see here.
So on the right is VIS-Sim, that's a traffic model, and over here on the left is the simulation that the drivers go through.
Yeah, this is the VIS-Sim model. Now, that wasn't necessarily linked, that was more example. Now I'm switching to a first-person driver's point of view. Now, you won't see the hood and the mirrors in this particular view. We can add the mirrors in there for some visualization examples, but because we have a real car cab, we project the images on the screen itself, and the hood takes care of that. And so we just really are used to collecting it this way. This is the same imagery that would be run, although it's going through this projector, it's a little bit lower resolution. A little mouse cam on here. You saw some pedestrians crossing the road there, and probably I'll move this on. So you kind of get the idea here. If you want to look at some more of the videos like VIS stuff, I can provide those later. So the next I want to talk about how we created some of the ARCA visualizations that we did. And for this, we had an exact location, where the DDI was also an exact location that we put. So we have many times we want to use exact location. Sometimes some of the research is human factors is not exact location. I'll show you an example of that later. So we need a real world location. We need to bring in that modeling and overlay the CAD designs for the intersection as it's needed by the roadway engineers. We wanted to use actual traffic counts that came from both the field, the study, and then we also used VIS and put in those actual traffic counts to make sure VIS matched vehicles per hour for AM peak traffic, for instance. And then the visualizations were created specifically to help with the public hearings. So we wanted to make sure we represented some locations that the public around the area, because the local people are the most ones involved for the intersections that are possibly going to be changed. And we saw a lot of people involved there. If you saw Wei's presentation, there was initially a lot of people were against trying to make this. They wanted much bigger, more expensive interchange instead. And let me go forward. If you're not familiar with an ARCUT design, it's just a quick overview of the left turn, the U-turn here, restricting the crossroad traffic here. It's not very bright here. And here's a view. I think this is the Maryland unsignalized ARCUT here. Kind of blow up from like the Google Earth. So what we've done is we've taken some of the Google Earth imagery, and you can see we use higher tessellation in the areas where we're really focusing on for the intersection itself. And we can go even more tighter mesh than this when we need to. Then what we've done is we've overlaid the CAD, and you can see this comes from the CAD design where it shows some turning circles and then paths for vehicles, which were kind of important. And we also take some of the signage directly from and place them precisely where they're located from the CAD. And we build everything from the sign sheet, so it's really pretty much visualizing. This is an example in the 3D editor of the signs for some of the locations. And then here's an example of, well, this is without the ARCUT. This is, we were doing compare and contrast for the public, so I won't leave this on very long, but Wei showed some very good examples from the field where the vehicles were crashing here. They're trying to go across. Here's the ARCUT. You've probably seen these videos when Wei showed them, and this is one of the places I'll probably speed up a little bit. This video is available as YouTube video now. Federal Highway is published, so you can get this online. It's not quite this resolution, but and here's the driver view. This was actually recorded from. It's a multi-pass process because we record a pass from the front view, and then we have the rear view mirrors recorded from what actually is output from the driving simulator. And we put them together in the video editing software. But this does represent the speed of driving. We put in there some algorithms to turn the head like the driver would need to see. So this is what we want for the public hearing, so that the people in the locality really understand what it means to drive this. And we're, I think, kind of pleased that it came out fairly good. Okay, interesting time. I believe this was also shown in the keynote, but this is kind of indicates how many projects for like the divergent diamond restricted crossing U-turn are really coming up as being places that are designing or even building across the country. I was very impressed. North Carolina is building, well, they built 20 and are planning 50 restricted crossing U-turns. That's a large number. And I'm sure that for their public hearings, they need to get through this process for the ones that are still in design phase still. And that's part of the Everyday Count program where the visualizations really help. now I'm gonna talk about the ATM study, which is active traffic management. And in this, we have some challenges in creating these signs here. In the field, we went and measured these, because almost everything we do in the driving simulator, we calibrate to real world as best we can. The projectors, you know, we got new projectors, they still can't match real world. Nothing can match real world, except the real world. And these LED-based signs are bright at 3 to 4 times what you can see for legibility distance of regular signs of the same size, just because of how bright they are. And this is a big challenge, especially in a simulator, where what we're doing is pixels, when you're far away, are becoming less and less pixels, and you have less pixels representing the same thing. And when you usually do that, the algorithms to figure out how bright to make the pixel blend and merge some of those sub-pixels, and you get more of a blur or a gray, where it was too white, you don't get a solid anymore. And what we've done is physically tried to model the LED signs based on light points. So every single LED that really is on one of these signs is actually represented. A lot of graphics processing required for this, so we couldn't have a huge amount in here, but for normal, typical highway usage, and we actually had a project that Utah did with this with our hardware too, where they did it for downtown Utah for a corridor, a whole corridor. They used these for alternate passing lanes, so at time of day they switch which way, not alternate passing lanes, sorry, the flexible lane change type hardware. But in this particular case, we wanted to study, this is behavior study of will people get over when the cars are driving on the road. These are also VIS generated traffic. Will the people get over when there's lane closed, and when do they go over? They recognize the signs, how far away, there's a lot of behavior issues there. And one of the things we did to make it harder for them and to see how well they did, these cars were driving more than 5 miles per hour and were late on actually modifying their speed, the VIS traffic was. How does the driver then change that? Apologize for some of the wiggling, that was a live capture of the drive. And you'll see there's an emergency event after the 2 lanes close. The other thing we had here was this confounding right lanes can exit and on the previous exit, but then there's the lanes are also closed, so they understand that, because this is actually done in the field, I think it's Washington State corridor. Some of these hiccups are because the computer's starting to have a little trouble with this. So, let's see. So I want to show, this is a photo of the way it looks on one of our monitors. So you can see that they come out pretty bright here, and you can see I'm even very far away in the distance with the signs. This is an example of the blurring that you get with traditional signage. And then this is with distance further away, where we aren't blending these light points, or they're becoming the dominant feature for the light points, which is the way light really behaves, because you don't have dark fading out the light, really. There's not a negative black photon out there. The photons are adding together still. So the only disadvantage of this is when you're really close up, it's not as bright as it really is in the real world, because we had to have a lower end for the, well, our projectors can't make them that bright either, but there's a lower end to keep this to match in the distance recognition, which is where we're really worried about. So just real quickly, I'll go over one of our ear projects is where we modeled a real location in Skaggsville, Maryland, and we heavily, I mentioned, use Google Earth, and we've started to heavily look at using Street View and trying to figure out what the roadway, well, this is the Street View, this is Google Earth, Google Maps actually in this case, but, and so we use those tools. We can export Google Earth directly into our 3D editing, and we can also then start that as the ground layer, base layer to add in some of the CAD models. And here is the video. Do I want to? No, there it goes. Video of the local. If you've ever, one of the challenges of this is we had field data that we're comparing with recreating the scenario for 3 different simulators. Our trees aren't as good as we often have in this, because we had to make trees that we're using proprietary software to make trees that we couldn't give to the other simulators. So our trees are worse than they normally look. But one of the challenges was the fact that this was a study done in 2002 in the field. We collected data. We had to recreate 2002. Well, one of the advantages of Google Earth is you have this timeline bar. We could go back to 2002, and they still had some pretty good data to actually look at and grab. for there was a lot less houses and stuff built around Skaggsville, Maryland in 2002 than it's really been built up now. But this is one of the problems with this particular roundabout when they first put it in. There's almost a reverse super elevation on the roundabout, throwing people off as they're going around the roundabout. And you could feel that in the driving simulator in the motion base. You could feel it kind of kick you out to the side, just like it did in the real world. So almost done here. Let's see. Oops. So some of the future stuff, we're really getting more and more into connected vehicle. We're doing human factor studies to help with like CACC, and we're doing projects for other things that are potential that we're looking at for having the human factors in the loop with the designs. We're also, some of the issues with driver acceptance of gaps with the CACC, so that's one of the things that we have to look at, and how do people go in and out of the platoons of vehicles, so that's some of the stuff that we're doing. Some of the other challenges that we have is doing the integration of the vehicle-to-vehicle communications, that we still have to solve some of these issues of bringing in, but it's stuff that's not undoable, it just takes a little bit of time and some programming. And then there's the other thing is that right now our vehicle doesn't have like glass cockpit. We're probably going to have to put one in to represent all these new displays that are going to be required for a connected vehicle, because you have to be able to give the information to the driver. It's a challenge in the real world, and they're designing these right now, so we have to have something that's flexible, because it's going to change on us. So we can't put something in there that takes a lot of effort to put in, and we just have to take it out and change it. And so we really have to create a glass cockpit that we can reprogram to represent what's in the vehicle. And then we also want to make sure that the way the connected vehicle, the way the vehicles actually drive for the braking, the dynamics, that we can actually represent that accurately for the motion and the motion feel with our vehicle dynamics as well. So with that, I almost caught up, and it's 5 minutes over still, but so any questions?
My watch that stops says you're on time.
Oh, okay. I was going by the clock.
Are there any questions? That was really great, and a lot of technical issues, right? You can understand and trying to use this simulator, and unlike other ones, this one, as you mentioned, is just very heavily oriented to the visual system rather than necessarily the motion base of the ride, because we're not trying to sell the car, we're trying to understand what the driver sees as they look out the window. Thank you very much.
I have a question.
Other speakers, thank you very much.
Oh,
Question.
Sorry, I was just curious, Jason, we've talked about this a lot over the years, and Joe, you've been in these conversations too directly. Do you see an evolution of your simulators, not just for the research aspects of it, but what I call the real living project, utilization of your simulators in the design and engineering process? You referenced something on the public involvement, but beyond just the public involvement, watching a recording of somebody in a simulator, but actually having a portable simulator as an integral part of the public outreach and engagement process, so they can experience these projects.
well, the visualization is more than just a public hearing. It is actually bringing design. We've been used heavily for innovative intersection work for that, such as DDI, ARCA, other types of intersections. And it's visualization not just for the public, it's visualization for engineers, localities, all the state DOTs that are actually needing this information as well, for them to understand from different disciplines, because visualization crosses disciplines for the most part. And yes, it is, I think we're behind in the US. Europe, and probably very quickly Japan, China, parts of the Orient are getting way ahead of using simulation as a design tool as well. I've seen that. We have European speakers coming over from TRB that say that they're using it all the time now in their university systems as well as in their DOTs. And I don't think we've engaged it where it can be properly. France has used it heavily almost 10 years ago for the design of some of their tunnels go through the Alps.
Yeah, I mean, even I was just playing right off of that, at the state level, we're talking about, traffic safety or truck safety, car safety, reaching out on that education component to say, I don't know, teen drivers, risky drivers that around trucks, for example. Hey, following too closely, or getting in front of a truck whose stopping distance is really long, those kinds of things that cars more or less crash when a truck is involved with in a crash. A lot of times it's with a car. Car is usually the contributing factor to that.
Right.
So, and the risky drivers' behaviors are usually tagged to, say, demographics that engage in risky behavior, like
Right.
teens. So it would be awesome to be able to get, like,
Well,
quick
driver-
video or something of what that really looks like and what those stopping distances are.
It's unfortunate that driver education was something the US tried to invest in simulators early on, like over 25, 30 years ago, and got burned.
Yeah.
And so the DOTs are very reluctant to sink money back into it, unfortunately. There's a few exceptions. I think the state of New Jersey's invested in some parts heavily
Yeah.
with some trainers, and they're starting to come around because it's getting so much cheaper.
Yeah.
And a game machine essentially is what you need
Yeah, right.
to do it. But yeah, it's. I also think that one heavy area where the same technology driving simulators do, it may not be driving it so much, but being able to visualize it
Yeah.
and control interactively
Right.
is these traffic control centers. For all the new ATM signage and all, they need to run the what ifs and see what happens in incorporating like simulation, traffic simulation ahead of time and quickly run to see what happens if they change their signs in a certain way.
Right.
And I think that's gonna be a heavy area that driving similar type technology can